Hello, everyone. Welcome to our webinar titled Solar-Driven Pyrolysis of Biomass, Insight, Experiences and Challenges in frame of the Horizon Europe project, PYSOLO. My name is Verena Kuhlmann, and I'm from the nova-Institut in Germany, near Cologne. And together with my colleague Anke Schwarzenberger, we are in charge of the communication, dissemination, and exploitation in the project. And today we are happy to welcome 5 researchers who will give insights into their work, experiences, and challenges in the PYSOLO project. So Marco Binotti, our project's coordinator, will give a short introduction into the project. Then Giacomo Lombardi from Record and José Manuel López from the Spanish National Research Council, CSIC, will give a tandem presentation about pyrolysis technologies. Then Martina and Neises-von Puttkamer from the German Aerospace Center will follow with her presentation about concentrated solar technologies for biomass treatment. And after her, José will take over again with his presentation from pyrolysis to analysis, techniques for understanding the products. And the last speaker will be Erico Kutchartt from the Forest Science and Technology Center of Catalonia with his insightful presentation on assessing agricultural and forest biomass to supply pyrolysis plants in Southern Europe using Earth observation data. So it is worth sticking with us until the end. Here are some housekeeping rules. We will have 5 minutes Q&A after each presentation. So please enter your question anytime into the Q&A field below. You know how it works, and address the speaker by using an at Martina, for instance, if you have a question for Martina, or you can also raise your hand if you want to state your question verbally, and then I will give you the right to unlock your microphone. And to make sure that we can cover all questions, we will have a final discussion after all presentations. And of course, all materials and the recording will be made available on pysolo.eu. And I would also like to draw your attention to our stakeholder workshop in November this year. We are about to plan, and if you want to know more about this, you are welcome to subscribe nova-Institut's newsletter to stay tuned. renewablecarbon.eu/newsletters, or follow the hashtag PYSOLO project on LinkedIn. Yeah, that's all from my side. Thank you, and I stopped sharing, so Marco, you can start sharing your screen. And I will introduce you. Marco Binotti holds a PhD in Energy and Nuclear Science and Technology. He's an associate professor of energy systems at the School of Industrial Engineering of Politecnico di Milano. His research with the group of energy conversion systems deals with techno-economic analysis and simulation of concentrated solar power systems, renewables, and advanced energy conversion systems. He has been involved in several European projects, and he is currently the coordinator of the Horizon Europe project PYSOLO on solar biomass pyrolysis. Marco, the stage is yours.
Thank you, Verena, for the nice introduction. I hope you can see the screen. Not yet?
Not yet.
Now you can see the screen, probably.
Yes, it's about to show up. Yeah.
Okay. So my duty here is to provide all the audience a short introduction about the PYSOLO project and let's say the framework for the subsequent talk, a very interesting talk about pyrolysis and solar concentrating system. So just to give you an overview of the project, the PYSOLO or PYSOLO acronym stands for Pyrolysis of Biomass by Concentrated Solar Power, and as the scope of integrating the CSP technology, so the concentrating solar power technology, and the biomass pyrolysis in an innovative system, which I will show in a very short amount of time. To do so, the project has started about 2 years ago, and it will last 4 years. So we are halfway of the project, which means that we have been starting with the experimental activity, as you will see. And the consortium is made of 9 partners from 4 countries that you can see here reported, while the coordination is done by Politecnico di Milano. So what's the idea under the PYSOLO project? Well, the idea is that pyrolysis is a process in which you have a thermal degradation of biomass in a temperature range which is between 250 and 700, let's say, in an environment, which means without any oxidizing agent. And the production of this degradation is bio-oil, pyrogas, and char. So a liquid, a gas, and basically solid carbon. So how this process is an endothermic process, so it requires heat. How typically the heat is provided to this process? Well, you can see it in this slide. Basically, what happens is that the biomass is dried, then you have the pyrolysis, and after the pyrolysis, you have the separation, for example, of the solid particle of carbon, the char, together with the particulate carrier. You have the combustion, and thus the combustion of this char provides heat to this particle that finally provide heat to the pyrolysis system. So this represents an inefficient step because we are using part of the valuable biogenic carbon produced just for combustion with CO2 emission. Of course, are carbon neutral emission, but in any case, we are, let's say, reducing the carbon efficiency of the process. Then what's the idea that moved us to the PYSOLO concept? Well, the idea is to provide the heat required for the pyrolysis with the solar tower system. So with concentrating solar power, which will heat up a solid particle, particulate carrier, as mentioned before, that can be stored, so can run night and day, and can drive the pyrolysis process. In this manner, basically, we will have an extra production of char, which was not present in the previous system. The advantage of having, let's say, a system of storing the energy allows to decouple the operation of the solar system and the operation of the pyrolyzer that can run, for example, even during the night. What type of operation we foresee for this system? Well, of course, the system can operate with solar radiation, but if we don't have solar radiation, we can also operate let's say, in self-sustained mode, which means that we can either burn, as in conventional pyrolysis, part of the char to run it during the night, or we can use, for example, electricity, low-cost electricity from the grid to heat up the particles instead of the solar tower. So when there is no solar radiation, we can use electric heating, in this case, induction heating. The other option is for this system to use the pyrogas produced in an internal combustion engine actually to produce electricity when the electricity price are high. So the idea is to have this PYSOLO plant as a very flexible system that can either use electricity, produce electricity, and produce, of course, bioproducts, or let's say valuable bio-oil, biochar, and in case pyrogas. So what we will do in the project, we will test different particulate carriers that should be optimized both for the operation on the pyrolysis and on the receiver side. We will test the key components of the system at TRL4, which means that we are testing not the integrated system, but each system per se, but with an eye on the entire optimization of the system. In particular, we will test the auger and the fluidized bed pyrolyzer, 2 different pyrolyzers in 2 sites at Record and CSIC. Then we will test the solar receiver at DLR. It's a rotary kiln type of receiver. We will test the induction heating and the separation system. Of course, it's also important to separate the valuable product from the particulate carrier itself. Apart from, let's say, this experimental campaign, we will have, of course, modeling activity supporting each component, let's say, study and development. And we will have a system at, let's say, analysis at system level in terms of techno-economic assessment, life cycle assessment, and risk analysis that will be performed within the project. So here it's briefly reported the objectives of this project. The objective is the validation at TRL4 of the solar pyrolysis process. So demonstrating basically the key components, and then we have objectives for each of the components. Objectives for the receiver in terms of operating hour and efficiency. We have a specific objective for the pyrolysis unit with specific target. We have objective for the particle charge separator unit, for the induction heating with KPIs and target, and for the overall system analysis that are here reported, but I will not go into the detail of this as the presentation will be made available for you. In the end, what we want to demonstrate is that this system is a full-scale system that can be a negative emission system on LCA basis. So not only carbon neutral, but given the fact that we are producing char, the overall carbon balance will be negative. That was a very short introduction because this was not the most interesting and relevant scientific part of the talk, which is, of course, part of the remaining webinar with all the experts from the PYSOLO consortium.
Thank you, Marco. And let's dive directly into the project with Giacomo Lombardi and José Manuel López. Giacomo Lombardi, PhD, is an R&D engineer at Record, specializing in thermochemical conversion of biomass and other residual feedstock into high-value bioproducts. Moreover, at Record, he is involved in the design and the operation of pyrolysis pilot units and consultancy services on thermochemical processes. He is currently dedicated to the activities of the project PYSOLO regarding the development of the pyrolysis unit for solar pyrolysis. And Dr. José Manuel López has been a keynote scientist at the Spanish National Research Council since 2023 and a member of the environmental research group at the Instituto de Carboquímica, CSIC, since 2000. He holds a degree in chemistry and biochemistry from the University of Zaragoza, the same university where he has earned his PhD in 2004. In his career in energy and environmental science, he has focused on sustainable solutions across three key areas: emission control, low CO2, hydrogen production, and waste valorization. The stage is yours, Giacomo and José.
Thank you, Verena, for the nice introduction. My and José Manuel presentation deals with pyrolysis technologies. In the first part of this presentation, we will have a look on which are the key parameters for the pyrolysis process. We will pass through the main differences for slow and fast pyrolysis. We will talk about of the heat demand and which are the heat supply strategies for these processes, and a look on which are the reactor concepts for slow and fast pyrolysis. In the second part of the presentation, we will show you the which are the pyrolysis reactors developed within the PYSOLO project, the slow pyrolysis auger reactor at Record, and the fast pyrolysis fluidized bed reactor at CSIC. Pyrolysis is a well-known endothermic process that is generally carried out in inert atmosphere or slightly oxidizing in a temperature range of from 400 to 650 degrees. Sorry. The main product for this process are carbonaceous solid, the biochar, a mixture of non-condensable gases, mainly carbon monoxide, carbon dioxide, methane, hydrogen, and other hydrocarbons with higher carbon atoms. And finally, condensable vapors that are a complex mixture of organic compound originating from the thermal fragmentation of the biomass constituents, which when condensed form the well-known bio-oil. Pyrolysis is generally classified into slow, intermediate, and fast pyrolysis according to the operating parameters. The most important parameters for the pyrolysis process are temperature, the solid and vapor residence time, and the heating rate, and biomass properties such as the size and shape, and the chemical physical composition, and finally the moisture content that affect the energy requirement for the process. Slow pyrolysis is characterized by lower heating rates and longer vapor and solid residence time, targeting biochar production. Generally, slow pyrolysis is performed on wood chips or logs. In fast pyrolysis, biomass is converted at very high heating rate for a short residence time, resulting in a high liquid yield up to 75%, the column on the right on the graph. In intermediate pyrolysis, the heating rate is lower than the fast pyrolysis, and the residence time of the feedstock can be in the order of minutes. And these operating conditions lead to much lower yield in comparison of fast pyrolysis and a higher yield of char and gas. In general, intermediate pyrolysis is adopted to make a balance between the three co-products. Well, talking about the heat demand, generally the heat demand for pyrolysis reactor includes the heat for biomass pyrolysis and the heat required to overcome the heat losses for the reactor. The last one depends on the reactor layout, whereas the heat for biomass pyrolysis for a lignocellulosic biomass in a temperature range within 500 to 550 degrees is within 0.8 up to 1.6 megajoule per kilogram. There are several heat supply strategies depending on the reactor configuration. In indirectly heated system, the heat is provided to the feedstock through the wall of the reactor using hot flue gas produced by the combustion of co-product for the process. Whereas in directly heated conventional system, the heat is internally provided by heating hot sand in a post-combustion chamber, oxidizing the co-product of the process. Exactly. The first method is the one generally adopted in slow pyrolysis, while the second in the fast pyrolysis reactor. The most common fast pyrolysis reactor are bubbling and circulating fluidized bed, the rotating cone, and the directly heated auger reactor. The essential characteristics for such reactors are the very rapid heating of the biomass and an operating temperature around 500 degrees, and the rapid quenching of the produced vapors. In most of this system, the heat is internally provided via solid heat carrier. The intensive mixing of biomass and the heat carrier intensifies the heating rate, which lead to a very high bio-oil production. up to 70%. In general, in fast pyrolysis systems, small size biomass is required to match the heating rate required for the bio-oil production. In slow pyrolysis is applied from rudimental batch kiln up to continuous industrial systems. In general, slow pyrolysis reactors tend to be simpler respect to the fast pyrolysis reactor, since generally are carried out with slow heating rate and high solid residence time. Nowadays, the traditional kiln have been replaced by continuous industrial reactors such as retort, auger, and rotary kiln. The retort are indirectly heated fixed bed reactor designed to handle wood logs and are not suitable for small size biomass such as agricultural and forest residues. Whereas rotary kiln and auger reactor are continuous moving bed that are less sensitive to the feedstock characteristics, making them suitable for all markets, so from the biochar production up to charcoal production. Within PYSOLO project, in particular within Work Package 2, Record and CSIC develop two different pyrolysis reactors to match the objective of the project. Record develop a slow pyrolysis auger reactor, while CSIC develop a fast pyrolysis fluidized bed reactor. With regard to the Record slow pyrolysis unit, is based on the auger technology. That is one of the technology that is less sensitive to the feedstock type, making suitable to convert non-homogeneous material such as pruning, agricultural and forest residues. This specific pilot plant have been designed for a feedstock feeding rate of around 1 up to 5 kilogram per hour and a heat carrier to biomass mass ratio within 3 to 9. The max operating temperature is around 650 degrees, and the solid residence time can be within 5 to 60 minutes by varying the rotational speed of the auger. So this type of plant is really a flexible unit that let us to investigate all the operating parameters into this reactor. The process heat is supplied via the feeding of the heat carrier that are heated within an electrically heated vessel, while the heat losses are compensated by electric heaters located along the reactor cylinder. Biochar yield that can achieve is around 30% with lignocellulosic material, and on the picture on the left are highlighted the main components of the plant. The biomass feeder on the top, on the right, the particulate carrier hopper and the electrical heating system for the particulate carrier, the reactor auger that is covered by the insulation, and the water-cooled screw that allow the solid at the outlet of the plant being cooled for a safety storage, and finally the solid tank. In this slide is reported the basic block flow diagram of the plant. The feedstock and the heat carrier are introduced into the slow pyrolysis plant by means of two different microfeeder. The heat carrier is introduced into the reactor hot, so it's heated inside a cylinder. The screw reactor perform the inner pyrolysis by introducing also nitrogen as purge gas. The rotational of the screw allow the biomass being heated along the reactor, and finally the solid and the so the mixture of the char and the heat carrier is collected at the outlet of the plant, and it's being cooled by means of a water cool screw and then collected for a safety storage into a stainless steel vessel. Whereas the pyrolysis gas are withdrawn from the reactor and cooled and condensed into a condensation unit that is basically made up of three surface heat exchanger followed by an electrostatic precipitator for the collection of aerosol. The condensates are recovered into glass bottles, and these condensates tend naturally to disappear into an aqueous phase and into an oil phase. The aqueous phase is generally rich of water-soluble organics, while the oil phase rich in heavy tar compounds. And finally, the clean non-condensable gas flow rate is measured by a volumetric counter at the end of the condensation unit, and its composition is measured by means of a micro-GC apparatus before being vent out. Finally, I would like to point out which is the main challenge for such a reactor. In order to use the char for agricultural purpose and to recirculate back to the solar receiver the heat carrier, a separation unit is needed to separate the produced char from the sand. And within PYSOLO project, we are developing unit that will allow us to separate these two fractions. So we will collect the char and the heat carrier separately, and this type of unit is based on the fluidized technology. So by means of the injection of a fluidization agent, we will be able to segregate on the top the char and on the bottom the sand that will be collected separately. And this separation unit will be tested with the previously generated solid from the pyrolysis reactor. So now I give the floor to José for the next part of the presentation. So José, the floor is yours.
Okay, thank you, Giacomo, and thank you, everybody, for coming to this seminar. In this second part, I'm going to talk a little bit more about the fast pyrolysis reactor that we are developing and using in the CSIC, that is based in the fluidized bed reactor technology. As you can see in this slide, the fluidized bed reactor is a type of reactor where the solid particles are suspended by a gas or a liquid, mainly by a gas, but making the mixture behave like a fluid. This fluid-like behavior and the large surface area on the fluidized bed facilitate an efficient heat and mass transfer between the fluid and the solid phases, what allows us for that fast heating rate and fast pyrolysis. The mixing action within the fluidized bed promotes a uniform, there's another advantage of the fluidized bed reactors, promotes a uniform temperature distribution, so we can prevent the appearance of hot spots in the reactor, and also allows for a continuous operation. As you can see in the slide, there is a presentation of the main forces like the gravity and the drag force that makes the fluidization gas to the particles. So when these forces are equal, or the drag force is higher than the gravity force, then we move to a fluidization regime. If you can change the next slide, please, Giacomo. Yeah. This fluidization behavior depends on different key parameters. The main one is the minimum fluidization velocity. So that's the superficial gas velocity at which the solid particles start to suspend and behave like a fluid. It can be calculated by theoretical equation, the Ergun equation, that takes into account different properties of the solid and the fluid, but also it can be calculated experimentally, that I will show later in our reactor. Depending on the superficial gas velocity, we can start from a minimum. When we reach the minimum fluidization, we have a smooth fluidization regime. And if we increase that gas velocity, we will start to have different regimes like the bubbling fluidization, slugging, and turbulent. The last one is when you have too much velocity, so the solid are pneumatic transport outside of the reactor, and you have to develop different collection systems to recover the solid. In our case, we are working in the bubbling fluidization regime. That is one of the most, I would say, good performances for the mass and heating transfers. If we move to the next slide, we will see the next key parameters that we have to take into account. It is the pressure drop inside the reactor, that it depends on the weight of the particles and the void within the bed. One engineering that has to be very well designed is the distributor plate. That's the plate that is going to distribute the inlet gas or the liquid, and because it needs to provide a uniform gas distribution to prevent the formation of slugs and channeling inside the reactor, inside the bed of the reactor, and also the reactor geometry. In that part, one design point that must be taken into account is the freeboard, is the section above the bed, just to prevent the particle illustration. We need time to, it's just to avoid the entrained flow, and that particles will be moved out from the reactor. This kind of reactors are, if we pass to the next slide, sorry, Giacomo. It's widely used in the petrochemical industry, for example, for fluid catalytic cracking and hydrocracking, and in waste treatment, in incineration or gasification of waste materials, and also in power generation. The main disadvantages are, compared with other technologies, are the high capital cost, because they have a higher initial cost compared with the other reactor types. The erosion and attrition processes that can suffer the particles of the bed. So we need particle recovery systems, and also the complex design and operation. In the next slide, I'm going to show you the CSIC fast pyrolysis reactor. In this one, you can see a diagram that's to show the different parts of the reactor. We have the dense zone where the bed is located, that is 20 centimeters high, and then we start to pass the fluidization gas with, in our case, is nitrogen, preheated before going inside the distribution plate, and then we can transform this fixed bed into a fluidized bed with a riser of 100 centimeters, just to allow the particles not to allow the particles to interchange to produce the mass and heat exchange, and also to be sure that most of the particles are not passed through to the condenser. In the condenser, we condensate the non-condensable gases, and we get the pyrolysis oil that you can see in the picture. And also just in the part that separate the dense part of the bed and the riser, we have an overflow to recover the biochar and the heat carrier. We have two feeders, a biomass feeder for the fuel, and a PHC feeder for the heat carrier. And as we are testing at this moment two different carriers, it's sand and bauxite, and we have calculated also the minimum fluidization velocity, both theoretically and experimentally. And we are working now we have achieved that the minimum fluidization velocity in the case of sand is 120 normal liters per hour of our fluidization gas, and slightly less with the bauxite. We can control all the heating elements of the reactor. We have also flow controllers to control the different flows, not only for the gas for the fluidization gas, but also for gases in the feeders, for example, and different temperature sensors to display and control the temperature in all the process. Pressure sensors. We can work with a biomass feeding rate from 0.7 to 1.5 kilograms per hour, and a PHC feeding rate up to 8 kilograms per hour. At the moment, we are working with pine wood chips with a particle size around a few millimeters, from 1 to 3 millimeters. And in the next slide, I will show you what's the real picture of the instrumentation of the pilot plant and the challenges or key parameters that we are studying and trying to maximize the conversion of products and the yield in bio oil production. That's in our case in the fast pyrolysis. We are going to try 3 different process temperatures from 450 to 550. Also, the way that we are we are feeding the heat carrier in a high flow rate with a low temperature difference between the pyrolysis and the heat carrier, or in the reverse way, using a low flow rate but a high difference of temperatures. That also can have influence in the properties of the conversion products. Also, using different fluidization velocities, we are also changing the gas residence time, minimizing the residence time just to get the maximum bio oil yield, and of course the type of PHC. We are using at the moment sand and bauxite, but one of the points or the key points is also trying to use calcium oxide and the biochar, because they can have catalytic properties in the process, so we can change the composition of the bio oil. Because in my next presentation, I will talk a little bit more about the challenges of the composition of the bio oil that we are getting from lignocellulosic biomass. And I think with this, I would like to thank all the partners in the PYSOLO project, and we are ready for any questions.
Thank you both. There was a question, and I think that Marco already wrote an answer, but I will read it for you to contribute. I have a question regarding the energy balance of solar-assisted pyrolysis systems. As Giacomo mentioned, pyrolysis is an endothermic process requiring an external energy source to sustain the reaction. Has your team conducted a detailed energy balance analysis for the system? Specifically, how much of the required energy input is effectively supplied by the solar resource, and how does this influence the overall system efficiency or energy yield? Are there any data or insights on the thermal efficiency or solar conversion performance? Would be greatly appreciated. You can see the question too, right, Giacomo and José?
Yeah.
Quite long.
Yeah, it's quite long, but I think I got the questions. On record, we'll provide partners with all the insight about the slow pyrolysis process, and the CSIC group will be done the same for we do the same for the fast pyrolysis plant. So we will be able to collect everything regarding the energy requirements for the pyrolysis plants. Colleagues at Polyme will carry out all the modeling about the pyrolysis process, and will got the input from the experimental activities to model the whole project. And also the group of Professor Binotti is carrying out the analysis of coupling the solar receiver with the slow pyrolysis plant. And the balance is that the overall process is sustained by the solar receiver thermal output. So we have I think I don't have the data about the efficiency, but maybe Professor Binotti can provide the person who did the question about that. Marco, I don't know if you can.
Yeah, I suggested all the audience to write the question in the Q&A, so it will be easier to address them. But in any case, I send a link to a paper in which we are performing some techno-economic assessment of the system. In general, for a 10 megawatt system, more or less the contribution for the pyrolysis is about 1.72 megawatt. So this is the amount of heat which is required to run the pyrolysis. In a conventional system, this will be provided by burning the product, while in our system is provided by concentrated solar power. The definition of efficiency, let's say it depends on how you define the efficiency, but considering also the auxiliaries consumption and all the electric consumption of the system, not only the thermal input and so on, you can get to efficiency of about 80%, more or less. If you are considering as efficiency, let's say the ratio between the lower heating value of the products divided by the lower heating value of the biomass plus the solar plus all the auxiliaries consumption. And I hope this clarifies the question.
Okay, thank you. Then there's another question for you, Giacomo.
Yeah, I read it, and regards how pure can be the biochar at the outlet of the plant. And let's say this is the challenge for the separation unit development, because we are currently working on that in order to increase the separation efficiency of char. We are currently evaluating the content of sand into the biochar, and the opposite. So the content of the biochar into the sand back to the solar receiver. At the moment, we got a separation efficiency of around 75, but we look to improve the separation efficiency by doing several steps in order to obtain a quite poor material, in order to match with the generally the guidelines for the use of the biochar as agricultural improver. So it's something that we will investigate within the PYSOLO project, the purity of the co-product at the outlet of the plant.
Okay, and one last question. Has there been investigation on the difference between the quality of conventional biochar and PYSOLO biochar?
Yes, this will be addressed within the PYSOLO project, because we will carry out a baseline test where we will convert the pine wood in conventional pyrolysis, and we will compare with the one produced by the injection of the heat carrier. So we will compare the two different biochar produced, the one from the conventional and the other separated with the separation unit, with the modified plant.
Okay, thanks. So let's go to the next presentation from Martina. You can stop share. And Martina can share. Martina Neises-von Puttkamer is co-head of department at the Institute of Future Fuels at the German Aerospace Center in Jülich, Germany. The department is focused on the design and operation of mini plant facilities and supports industry in the development of commercial facilities for the production of sustainable energy carriers and raw materials. She holds a PhD in mechanical engineering from the RWTH Aachen University and has been at Zurich for a postdoc in 2013. Overall, she has more than 15 years experience in the field of concentrated solar power and concentrated solar thermal. Applying concentrated solar heat to higher temperature process, such as solar fuel production, solar metals recycling and processing. Thank you, Martina, and the stage is yours.
Thank you very much, Verena. So first of all, you should be able to see my slides and also hear me well.
Yes.
Perfectly, thank you. Okay, then let's get started. I'm happy to be here and to talk a bit now about how we bring the sun actually into the treatment of biomass. So we will start with a very brief introduction about solar concentrating technologies, and then we'll have a look at how to connect these technologies into specific chemical applications. In the second half of the presentation, we will look specifically in the biomass treatment, and then we'll end with a look on the PYSOLO concept and how we want to integrate it specifically in this process. So let's get started. The concept of concentrating sunlight is actually very, very simple, and you all know it from school, from your physics education. So you can concentrate sunlight with a concentrating optics, can be a lens or a curved mirror. These concentrating optics create a focal point, and in the focal point, it gets hot. So what happens when we concentrate sunlight? Well, basically what we do is we increase the energy density. And by increasing the energy density, we can increase the temperature. Depending on the degree of concentration, you can reach temperatures up to 1000 degrees Celsius or even higher. It gets more complicated the higher your desired temperature is, but in theory, it's principle. So there are different types of concentrating technologies. They all have some components in common. The first is they all use mirrors to redirect and concentrate the solar rays. Very important for us working with concentrated solar technologies, we can only focus and concentrate the direct solar irradiation. So all the other irradiation is not useful for us. So the mirrors, as I said, they focus the irradiation. Then in the focal spot, we typically place a component that we call absorber or receiver. As the name already implies, it absorbs the solar radiation. And then the third component is usually use a heat transfer medium to basically take away all the energy and also to make use of the energy in the end. The heat transfer medium can be a gas, but also can be a liquid or even solid, as we will see in the course of the presentation. Now, one very important parameter that we usually use to describe these concentrating systems is the so-called concentration factor. The concentration factor is the ratio of the flux density after the concentration to the flux density before the concentration. And it is directly connected to the temperature. So to keep it simple, the higher the concentration factor, the higher the temperature you can reach. Now let's have a look at the different concentrating solar technologies. Let's start from the left and go to the right. So the parabolic trough technology and as well the linear Fresnel technologies. Maybe you have seen them on TV or on reports. Parabolic troughs are commonly used nowadays for production of electricity. So-called parabolic trough power plants. Those two systems we call line focusing systems. That is because they create a focal line. They don't have a focal spot, but a focal line. And they have a concentration factor of up to 100. This is because of their special focal line instead of a focal spot. If you want to concentrate higher, then we go to the right technologies, the so-called solar tower or the parabolic dish. The solar tower consists of mirrors that we call heliostats. Those mirrors are placed on the ground and they reflect the sun onto a special target at the top of a tower. We call it a solar tower. And here at the solar tower, we place the receiver or the absorber with a heat transfer medium to create the heat that we need. So these systems we call point focusing systems because they actually create a focal spot. The concentration factors here are much higher compared to the line focusing systems. The solar tower can reach concentration factors of 1000, and the parabolic dish can go even higher because due to its special design. For all of these systems, it is necessary to track the sun in the course of the day because, you know, the sun moves along the sky in the course of the day. And in order to efficiently concentrate the direct sun, as I mentioned, it is necessary to track the sun during the day. That means the mirrors usually are movable and basically follow the sun throughout the day. Now, as I said, the concentration factor is also related to the temperature. That means if you look at the temperature ranges that can be reached by these different systems, we can say roughly that with the parabolic trough and linear Fresnel, they operate usually between 400 and 550 degrees C, depending on the heat transfer media they use. And then if you look at the solar tower, it usually operates between 600 and 1000 degrees C. And the parabolic dish is not used so often, but as I said, here we can even go higher in the concentration and temperature range. So now we have our concentrating technologies that in the first place provide us with high energy densities and in the end with high temperature heat. So now how do we couple this solar energy into a chemical process? In principle, we say we have two different concepts available. In the first concept, we have two components. The first is the receiver and the second component is the actual chemical reactor. Now here in the receiver, the solar irradiation hits the receiver, a heat transfer medium, usually an inert one, flows through the receiver, is heated up by the solar irradiation, then it is transported to the chemical reactor, and here the energy is transferred from the heat transfer medium to the reactant, and then this drives the chemical reaction. So the second concept we call a direct concept, and you can see immediately here we have only one component. We call this component receiver reactor, and the name already implies that now this component does both. It is the absorber or the receiver for the concentrated solar radiation on the one hand, but it is also the chemical reactor on the other hand. So the reactants flow through this receiver reactor and then the chemical reaction takes place here at the same site. And now you can imagine both concepts have their pros and cons. And for the individual application that you're looking at, it's not always so easy how to decide which system to use in the end. So what do we do when we want to decide looking at a specific application? First of all, we ask the question, what concentrating system can I use? Well, the first parameter you look at, of course, is the temperature. You can say roughly if you want to operate your application, let's say above 600 degrees Celsius, you have to go with a point focusing system. So often then we choose a solar tower, for example. But it also depends on other parameters, for example, of the size of your plant, on the amount of products or the amount of material you want to treat. So there are a lot of parameters coming here into play when you decide on the concentrating system. And then the next question is, how can I connect the concentrating technology and the chemical process? And here it's important to look at the actual chemical reaction you're targeting. What is the temperature range and what is the pressure range that it needs to be operated? What are the reactants and the materials involved? For example, are there special gases? What are these materials? Do I need to include a catalyst into my system? And then you have to ask, okay, can I operate an open system, or does it have to be a closed system? And what is the process operation I want to have in the end? Do I want to operate continuously, or am I looking at a batch process? And then in the end, you can think about the different concepts and ideas. What can the reactor or the receiver reactor look like? And now we look a bit more into detail in the pyrolysis reaction. So we already heard that the pyrolysis reaction is operated in inert atmosphere. This is very important. That means we need to operate in a closed system, and it has to be gas tight. We also already heard about the reactants and the products. Reactants is the biomass, and the product is biochar, bio-oil, or gas. The temperature range depends very much, but it is between 300 and 900 degrees Celsius. And here we are looking at an operation at atmospheric pressure, actually. So now we have these prerequisites, and now basically you can play around a bit and create ideas how your system can look like. Let's think about a direct solar receiver reactor. So in this receiver reactor, we would have the biomass entering here, the reaction taking place inside the receiver reactor, and then the biochar, oil or gas exiting the reactor. In this concept, we would need some kind of a window to close the whole receiver reactor, because we learned we need to operate in a closed system, and we need to make sure that no air comes in and disturbs the reaction. So that means we would close the system here with a window. These windows usually are made out of quartz. These quartz windows are a little bit of a peculiar component because it looks very simple in the first place, but then they turn out to be a really, really difficult component in the overall system, because quartz glass is very, very sensitive to temperature gradients. It really doesn't like temperature gradients. It doesn't like if it gets too hot, and especially it doesn't like hot spots. And now when we think about our reaction, so the pyrolysis reaction, we produce tar and char. So here it's the risk that these products, they stick to the window. And where they stick to the window, they can create hot spots, and then the window would break. And the moment it breaks, you can pretty much shut down the whole system, because then your system is not gas tight anymore. So this is a very high risk. And also the creation of dust in the reactor due to the char. There is a risk that this will block the radiative heat transfer. Okay, so let's keep this in mind, and then now think about an indirect concept where we have a receiver operating with an inert heat transfer medium and the chemical pyrolysis reactor. So now here it's for us clear from a thermodynamic and heat transfer point of view. It's clear that we need to operate the receiver at a higher temperature. Then we will operate our chemical reactor, because obviously there will be energy losses on the way here. And thermodynamics just says the T here in the receiver needs to be higher than the T in the chemical reactor. That means we need to take account for this. Also here in this system, the tar might deposit on the inner surface of the chemical reactor, which might reduce the heat transfer. The good point about this concept is that here we can possibly include storage into the whole system. You can think about putting storage tanks here on the cold side as well as on the hot side, and these storages would give you the possibility to operate the system even after the sun has set. So now, as you already learned, for the PYSOLO concept, we decided to go with this indirect system due to several reasons. And here, basically, this is how the concept looks like, as you've already seen. Our part now is to focus here on this solar part. So we will operate, and we are designing and test, and we want to test solar receiver that will be operated with a particulate heat carrier. There has been intensive work from my colleagues to investigate and to characterize many different possible particulate heat carriers, such as olivine, bauxite, silicon carbide, and sand. And I will not go into any details now. If you're interested here, there are already publications available that we would be happy to share with you to see how these different heat carriers compare to each other. So here our receiver that will be placed later on in a, when we think about the pilot plant on the top of the solar tower, the cold particles will enter the solar receiver. The receiver is designed to operate in a temperature range up to 800 degrees C. As we use an inert heat transfer medium now, we are able to operate open under atmospheric pressure, so basically also under air. Only for some tests we design it to be closable, but this is really just for the for the project, and will not be the case later on when you think about any pilot plant application. In this system, it is very important also to consider that we will have 3 more components that we have to take care about. The first is that we need to transport our particulate heat carrier. The second component is the storage system. As I already said, there can be a cold storage tank and a hot storage tank to be more flexible and independent from the actual sun's irradiation. And the third component that's very important in the pyrolysis reaction is the particle air separator, because we learned the pyrolysis reaction needs an inert atmosphere, so we need to make sure that no air in the end enters our pyrolysis reactor. That means we are at the moment also designing specifically this particle air separator to make sure that the air basically exits the system before the particulate heat carrier enters the chemical reactor. And now, what is the idea of the solar receiver in the end? So the concept itself is actually quite simple. We decided to go for a solar heated rotary kiln. A rotary kiln is a concept that is used also widely in the chemical industry, and now we kind of adapted to run also with concentrated solar irradiation. So here in this concept, we will have basically, it's a drum that rotates. You will have the particulate heat carrier entering on one side. And then once it enters, it is also mixed. And at the same time, it moves through the kiln. It is irradiated with the concentrated solar irradiation and heated up while it moves through the kiln. And then at the end of the kiln, it exits again, and then the whole journey continues. We go to the particle storage, then the particle air separator, and finally the heat carrier enters the pyrolysis reactor, and then the whole cycle starts again. And now this is the first concept or drawing of our idea of the rotary kiln, of the solar rotary kiln. We are actually now finishing the design phase. So this is why at the moment I can only provide you with some first designs. Next year, hopefully we can show some actual pictures of our receiver in place. But in principle, the receiver or the whole system is divided into 3 components. The first is the particle feeder. Here the cold particles enter, and then they are fed into the actual rotary kiln. Now this part here is the one that rotates. The particles move through the rotary kiln, and then here at the end is the third component, the particle accidental collection. So now, as I said, the concentrated solar radiation enters here through the aperture, it's open, it hits the walls as well as the particles or the particulate heat carrier here in the bottom, and then through diverse heat transfer mechanism, the particles are heated up to about 800 degrees Celsius. The diameter I put here of this outer shell is 560 millimeters, and the whole receiver is designed to operate with 15 kilowatts. On aperture, we say that means 15 kilowatts entering here into the receiver. Now, you might wonder also about the rotational speed. That means the speed that the drum will rotate in the end. Well, this will be part of the testing, actually, to adjust the rotational speed in such a way that the residence time of the particles here is long enough to guarantee high enough residence time so that they can heat up to the desired exit temperature. Now, as I said, we are about to finish the design phase, and our next target is to have everything ready and in place. And in 26, we will test the whole system in our test facilities of the DLR in Cologne. The solar receiver, as I said, is one of the main components and part of our work, but we also plan to test the air separator and the transport system separately also in the next year. So now I will end by showing you or giving you a little bit of an insight about the test facilities that we have available at DLR in Cologne and that we will use in the course of the project. The first test facility is our solar furnace. Now, this is really a test facility specifically designed to create high concentrations for testing any kinds of applications you might think of. It consists of a heliostat, which is basically just a plain big mirror. The heliostat redirects the irradiation and it hits a so-called concentrator. And this concentrator is now composed of more than 100 small mirrors that are curved. And these mirrors actually redirect and concentrate the sunlight, and they redirect it into the building. And now here behind this opening is an experimental room where the receiver will be placed, and it can also be connected to all the auxiliaries that are necessary. So this is our facility where we use actual sunlight. We also have a facility we call the solar simulator, and you might already imagine from the name, here we simulate the solar irradiation to be able to operate more independently from the actual sun. We are here in the west of Germany, these test facilities, so you might imagine that having really, really good sunny weather conditions is not always easy. That's why we decided to also have this solar simulator for operation and testing of our components. The solar simulator actually works with xenon arc lamps, and the light of these xenon arc lamps is very similar to the sunlight. That means they have a spectrum very similar to the actual sun, and this is important if you want to simulate the sun. You have to make sure that your light source has a spectrum similar to the sun's. Now, this light of the xenon arc lamps is redirected and concentrated by these curved reflectors. And here in the solar simulators, we have 10. And now the light is concentrated onto a focal spot. And here in this focal spot, we can again place our experimental setups. And here in the picture, you can see actually a particle reactor that was tested some years ago in the solar simulator of DLR. And now, yeah, I will end now by giving a summary and a bit of an outlook. We saw different concentrating solar technologies that can provide different temperature ranges with temperatures higher than 400 degrees Celsius. We saw that we can connect them in different ways to a chemical reaction. And we also saw that in the PYSOLO project, we will have a solar receiver operated with a particulate heat carrier that will then be connected to the actual pyrolysis reactor. And now, yeah, we are very excited and looking forward to the next year because a lot of exciting work is coming up for us, especially the testing of all our components, the solar receiver and so on in our test facilities in Cologne. And this is actually a picture of another rotary kiln that was designed and tested for a different kind of application. But I hope next year we will be able to show you an updated picture with our functional solar receiver that we tested in the course of the project. So with this, I end, and yeah, looking forward to your questions.
Thank you, Martina. And you mentioned a publication, and it's already available on pysolo.eu. It's about the characterization of the particle heat carriers. So just to mention that. And now we have two questions for you, and the first one is about how does the temperature control in the direct reactor works?
Yeah, so it's not. So now let's start with the actual test receiver that we're building now. For this receiver, we are able to control the power input in our solar facilities. That means in the solar facilities, in the solar furnace, as well as the solar simulator, we can control the power input by different means. In the solar furnace, we have an optical shutter, you might call it, with which we can control the input, the power input. And in the solar simulator, you control it by switching on certain number of lamps. And you can also control the power of the lamps in a certain range, but that is very limited. So here, basically, we control it by switching on the different or a certain number of lamps in the end. And later on, when you think about, let's say, a pilot plant operated in a solar tower, here you work with the actual heliostat field. That means there is usually, or also today, when you have applications for power production, there is a control system running all the time for the control of your heliostat fields. And then this control system always decides, depending on the temperature in your receiver, like how many heliostats aim at the receiver at this particular moment. So yeah, it's a very interesting operational problem.
Okay, thanks. And the next question is: the rotary kiln operated under inert atmosphere, and is there an inlet to refresh the particles?
Mm-hmm. So the receiver will be operated in air because we have this particulate heat carrier that we will use. There is no problem to heat it up under air. So this makes the whole design much easier. So we don't need to have a specific window to close the system. So generally, the receiver will be operated just open under air. I forgot the second part of the question. What was it?
Is there an inlet to refresh the particles?
So in the end, in the design, of course, the particles will be circulated. So you will have the particles entering the pyrolysis reactor. And then after exiting the pyrolysis reactor, they will be separated again to be reused then in the receiver again. Of course, here for our tests next year, I think first of all, we will not close the whole cycle, but we will start basically with a big batch of particles that will then be fed into the reactor and collected at the end of the reactor.
Mm-hmm. And there just came another question. What about particle heat carrier contamination? For instance, char and tar residues that go with the particle heat carrier in the rotary kiln.
Yes. Actually, this is a very good question. And as far as I know, this also is part of the different investigations in the project. When the pyrolysis reactor is tested, then also we will get some feedback about the contamination that we can then also consider in our ongoing tests. So this is something I cannot answer today. It's part of the investigation as far as I know.
Okay, so we have to be patient. Okay, and yeah, thank you. By now, Martina, and the next speaker is José again. You have to
I'm going to share my presentation. Okay, just a second.
Yeah, and we need the presentation mode. Yeah, perfect.
Okay. Now you can see the presentation. Okay.
Yes.
Yeah. This presentation is the intention is to give you a view from how we link the pyrolysis or the products we get from pyrolysis to the techniques that we use to understand this kind of products. The overview, firstly, I will just give a brief introduction of the second generation biomass and thermochemical processes, the pyrolysis that we are using, and how that influences the pyrolysis products that we are looking for, and the properties that the properties of these pyrolysis products, how we can analyze or which kind of which range of different techniques we are going to use to analyze the composition and the properties of these products. So why are we using second generation biomass in the PYSOLO project? That's because we can reduce the food competition. This is a second generation biomass that we are not using food sources. Also, we are promoting the circular economy because we can convert agricultural, forestry, or even urban organic waste into valuable energy resources. And also it has linked some environmental benefits. We're reducing the greenhouse gas emissions gases. And it has the potential to develop a biorefinery just based in the products that we can get from the biomass. In the right part of the slide, you can see some of the principal thermochemical processes that we can use to convert the biomass, mainly the combustion or incineration, just to get heat and power with oxygen, combustion with oxygen, the liquefaction, that it's also it's done under pressure and using water and to get energy mainly, and also that we can get some valuable chemicals. Hydropyrolysis, in that case, we're adding hydrogen to upgrade the products that we are getting in the biofuel mainly. Also, the slow or fast pyrolysis that we will go deeper in the next slides. And carbonization, that is aimed to get a high quality char, more for the solid, that it will be more similar to a really slow pyrolysis. And of course, the gasification, when in this case, you are looking for the gas byproduct mainly, looking for a syngas that can be used to produce different chemicals or fuels. In the pyrolysis, that is the thermochemical process that we are studying in PYSOLO project. Sorry, what are the influence or which parameters we are going to influence or have an influence in the products that we are getting in the bio oil, the biochar, and the gas, and also in the composition, not only the yield of the products, but also in the composition. Of course, the first thing to have into account is the feedstock. We are using lignocellulosic biomass that is mainly composed by polysaccharide, two polysaccharide polymers, the cellulose and the hemicellulose, and also another biopolymer, the lignin, that is mainly based in aromatic alcohols. What's the problem with this heterogeneous composition, but also not only the different behaviors and properties of the polymers, but also the high concentration that you can see here in oxygen. This is one of the main differences when you are looking the oil that you are getting from biomass than the oil that you are getting from a fuel, from conventional fuel. This high oxygen content is going to give us really properties of the bio oil that are at disadvantage if you want to use it directly. because of this composition, or because of these disadvantages in the composition, usually the pyrolysis process is also coupled with other technologies. You can use copyrolysis of the biomass with other feedstocks that give us better properties to the oil that we get, or also adding a catalyst directly inside the pyrolysis reactor, and also some amounts of hydrogen, so you can get an upgrading of the bio oil in situ during the process, or also you can use upgrading processes ex situ afterwards, so like fluidized catalytic cracking or hydrocracking as well, so to get different biofuels or extract added chemicals, added value biochemicals from the bio oil. Why is this important in the PYSOLO concept? Because as we have seen through the previous presentations and also in the project presentation, we want to increase the product's yield, so that we don't need to use, most of the time we will not need to use the pyrogas or the biochar to get heat for the process, as we are getting the heat coming from the solar particle receiver and using heat carriers. And in this way, we can maximize the added value product that we get. So mainly, we are focusing the biochar and the bio oil, because the pyrogas is going to be used mainly to get electricity in a combustion engine. And in this way, we increase the carbon efficiency and reduce the CO2 emissions. But to accomplish these objectives, we need to characterize properly the composition of the three products that we are getting. So we can decide if they can be used for market and refinery, or it cannot be. It depends on the composition. The three different byproducts that we get from pyrolysis are, as we have been talking during these presentations, the pyrogas, the bio oil, and the biochar. And going through the different products, and starting by the pyrogas. It's non-condensable gases that are mainly, the composition is carbon dioxide, carbon monoxide, hydrogen, methane, and another light hydrocarbons, and in really small amounts, heavier hydrocarbons and ammonia on sulfur and nitrogen oxides. The composition of this pyrogas is going to give us the possible applications. The low heating value of the pyrogas is lower than the natural gas. That is due because the main products in the pyrogas are CO2, CO, and less hydrogen and methane than in the less methane, for example, than in the natural gas. But in any case, with this composition, we still can use the pyrogas for heat or electricity production in a gas combustion engine. They can be used directly or co-fired with coal, for example. We can try to change some pyrolysis parameters to increase a little bit, maybe adding some oxygen in the process, or a small amount of oxygen or hydrogen to get increase the composition in hydrogen and methane. Depending on the CO and hydrogen ratios, we can use it also as a syngas to produce biofuels. But in the conventional pyrolysis process, the main application of this pyrogas is to be burned to get process heat. In the PYSOLO project, it will be used for heat or electricity production. I'm sorry. In the case of the biochar, it's mainly carbonaceous residues with a main the main component is carbon up to 96%. It can have also some unconverted organic solids and a mineral fraction. That mineral fraction is very important to know the composition, because if we want to use the biochar as a soil amendment or for carbon sequestration, but in the case of soil amendment, we need to know the amount of macronutrients that can be still in the biochar coming from the feedstock, from the lignocellulosic biomass, like nitrogen, phosphorus, potassium, calcium, magnesium, or sulfur. And also we can found some micronutrients that are useful for the crop development. It has the main composition is carbon. It has a high heating value, similar to coal, so it can be used for fuel applications, as it was used mainly in the or burned to pyrolysis to get pyrolysis process heat. That is in the main use of this biochar in the case of conventional pyrolysis. But as in PYSOLO, we are going to use it mainly for soil amendment and carbon sequestration. And also the development of surface area in the process of the pyrolysis, we can use also the biochar as a precursor for active carbon that can be used as adsorbent to remove pollutants from air currents or gas fluids, and also for filtration in water treatment. But in the case of the main product that we are going to get in the fast pyrolysis, for example, up to 65% of the bio oil, this is the most challenging product of the biomass pyrolysis, because it's a big mixture of up to 500 or more compounds, mainly with oxygen compounds. So it means acids, alcohols, ketones, aldehydes, phenols, etc., with really small or smaller amounts of alkanes and aromatics than if you compare with a diesel or a gasoline fuel. And also we have the water, not only the water present in the feedstock, but also water produced during the pyrolysis process. This is, if we go deeper in the composition of the bio oil, we can see that we can find up to 30% of water. So mixed with a high oxygen content, that it can be up to 40%. It makes have a low heating value, high heating value of the bio oil compared with the fuel oil. It's half of the value. And also it makes non-mixable with conventional fuels. Due to the acids present in the bio oil, we also have a really low pH and a total acid and a high total acid number. So we can find problems of corrosiveness of this product, not only in our facilities, but also in the afterwards in the refinery. Also, due to the oxygen, we have a poor stability. We can still have polymerization reactions during the storage of the bio oil. And as I mentioned before, we have low aliphatic and aromatic content in the bio oil. So for fuel applications, we need an upgrading of this bio oil. It could be catalytic cracking, reforming to get a gas fuel, or high pressure hydroprocessing to increase the amount of aliphatic and aromatic content. And also we can extract some added value chemicals like phenols for the production of resins, some additives used in fertilizing, or flavoring agents. But as the title of the presentation means, is that to know the final application, or we need to have a deep characterization of these the three products. I have here a list of different techniques that can be used for characterization, and also I have highlighted the PYSOLO capabilities. So for the gas, we can know the complete composition because we have the gas chromatography coupled with TCD to analyze all the permanent gases and the hydrocarbons that are in the pyrogas. And from that composition, we can calculate the lower heating value. Also, we can analyze the sulfur content, not only the hydrogen sulfide form, but also in other different compounds. For example, we can increase this sulfur analysis to get the hydrogen sulfide, but also the carbonyl sulfide, methyl sulfide, and carbon disulfide. And we can analyze, as I said, the permanent gases in a GC coupled with a TCD detector, and also light hydrocarbons up to C5. In the case of the biochar, we can run the proximate and ultimate analysis, so we can have the elemental composition, and also very important for the metal, for the nutrients and the micronutrients, we also have an ICP coupled with atomic emission spectroscopy for the analysis of these metals. And also for the physical characterization, we can analyze the surface area, the porous structure, and also the crystalline phases of the biochar. So that in that way we can know the possible applications like active carbon. And in the case of bio oil, we can analyze a really big range of properties and compositions. We can analyze the water content. We can qualitative and quantitative identify the bio oil compounds, also calculate the different heating values, the sulfur and elemental composition, and also the acid number, density, viscosity, and the boiling range. As I said before, this is a big mixture of different organic compounds, up to 500 different compounds, and to one of the most powerful techniques to analyze this bio oil is we have two GCMS, two gas chromatograph coupled with mass spectrometry, and we can separate through the capillary column the different compounds and use the mass spectrometer to identify the different compounds, because each one of the organic compounds under the electron beam, they can break bonds in a different pattern. So each different compound has a fingerprint associated with it. So we can identify the compounds, and we can allocate all the compounds in families. So we can know the composition in phenols, for example, cyclic hydrocarbons, acids, and other compounds. Another powerful technique that we have is a simulated distillation with just one injection in the gas chromatograph. We can extrapolate, and with a calibration curve, the boiling point distribution of our bio oil. So we don't need to run a full distillation column to calculate the boiling point distribution, and compare with conventional fuels like gasoline or diesel. The main challenges or why we need all these techniques is because changing the pyrolysis variables, we are going to get different products and different composition in our bio oil. That composition depends on the temperature, depending on the flow rates, depend on the gas resident time. And also the last challenge that we want to face is that, as I said in the first presentation, two of the particle heat carriers that we are going to use, mainly calcium oxide and the biochar, we have observed, or we have in previous projects and previous research that these solids can have catalytic effect in the bio-oil properties. So we can run what we say an in situ upgrading of the bio-oil during the pyrolysis process. For example, the calcium oxide has allowed us to to increase the high heating value up to from the 20 to 30 megajoules per kilogram. We can reduce the acidity of the bio-oil. We can promote the oxygenation rate of 23%, around 23%. And all of this because calcium oxide can catalyze reactions like the hydration and the carbonization of the bio-oil products, components, sorry. And this is the preview or the full view of characterization techniques that we have and why are so important. And now I am open for different questions of the audience.
Thank you. Thank you, Jose. Actually, I cannot see a question for you by now, but maybe there will come up a question later. So I would suggest to go to the next presentation. And our last speaker is Erico Kutchardt. He is a forest engineer from the Universidad Austral de Chile, while with extensive international experience, including studies in Germany, Czech Republic, and Italy, where he completed his PhD. He has worked in several countries on forest inventory, remote sensing, and geomatics, and has led or contributed to numerous research projects. He is also active in teaching, supervising thesis, and is currently a guest scientist at TU Dresden and a lecturer at the University of Chile. At the moment, he is a researcher at CTFC, focusing on using remote sensing technologies to quantify forest resources for carbon accounting, biodiversity, and land use management.
Okay, thank you very much, Verena, for the introduction, and thanks to everyone for attending our webinar. Can you hear me well, right?
Yes, very
okay,
well.
Perfect. So now we will change to a completely different topic of the project. It's more about the geospatial information. And the title is Assessing Agriculture and Forest Biomass to Supply Pyrolysis Plant in Southern Europe using Air Observation Data. As Verena mentioned in my introduction, I am a researcher at the CTFC, and this work is done with Neos Puy in Nuria Cuilgué. So I will like to start with the, now it's moving. With this picture, so we want to produce green, clean, and renewable energy and products, like Jose Manuel was explaining before, oil, biochar, and so on. So with this picture, we want to summarize the main goal of the project and the main input. So we have solar energy, we have biomass. We want to get this product through the pyrolysis, but the main topic is where this biomass is allocated. So we were discussing a lot how to process the biomass, but where is this biomass? So here the project is about two types of biomass. We have forest one, divided in two groups, pine and oaks, and then we have the residual agricultural biomass. So internally in the consortium, we're asking what are the main crops. So we decide to work with the grape pomace and olive millways. So the target countries are Spain, Italy, and Greece. In the case of forest biomass, we start to see how spatially is distributed the biomass, the availability, so how many grams per hectare we have, and then we were thinking in restrictions. So I will explain more in detail in the next slides. Then we decide to carry out this multi-criteria analysis, so where we can identify the most suitable areas where we can establish this pyrolysis plant, and then to locate the best areas to store and to pre-treat the forest biomass. And then the agricultural biomass is based mostly in two crops, which are olives that we use to produce olive oil, and grapes that we produce, and wine, of course, we produce residuals. We were quantifying this crop based on local land use covers, and then it was very important to quantify. So with the yield, we can know how much kilograms we have per hectare annually, and we have this information by province and region in each country. And then to localize this main crop is mostly to the producer. So who are the main producers of olive oil and wine. This is just an example when we visualize the distribution of biomass. Some areas looks very promising, like for example, here in the north part of Italy, we have high biomass availability, but there is lack of sunlight. So this is not good for our project. And here, for example, we have high biomass availability, but they are focusing other type of species that they have another market, and this part of Galicia is mostly eucalyptus, which are not target species for PYSOLO. Here we have an example in Greece. So we have high biomass, but are located in protected areas. You know that in Europe, we have Natura 2000, which harmonize the protected areas in Europe. So when this, we can have high amount of biomass, but can overlap with these protected areas. And here in Italy, which is the country that has the highest amount of biomass, this is between Trento, Bolzano, but it's a steep terrain. It's very hard to mechanize the biomass. But here we have a good example in the south of Italy, where we have a good compromise between high biomass and good solar irradiation conditions. This is how the DNI, this direct normal irradiation, is distributed among the countries. We have this table just to understand more or less the level, but at the end of the story, even if it's classified in these 6 classes, we were normalizing this variable, and the important thing was to discard areas that we have less than 1,000 kilowatts hour meter square. This is our workflow that we were applying for forest biomass. First, we were using biomass map, but we have different options from the European Space Agency. Here, CTFC developed one biomass map using satellite data and artificial intelligence. But then you have all the biomass. So we want to know only the forest biomass, not agriculture, not the grassland. So we select only forest areas. So this was our output 1. So once we have the total forest above ground biomass, we start applying restriction. Why? Because, for example, about the topographical features, we have a slope elevation. So we have steep terrain, high elevation. It's very hard to mechanize to extract the biomass. We can do it, but it will be very expensive. We have very low productivity and very high cost. Also, we cannot intervene in soils that are quite fragile. We cannot put any machinery, not harvester, no forward. And also the forest cover is important, because if we have, like, for example, 50% of forest cover and we are cutting more, we start to have degradation, and the protected areas that I already mentioned. So once we apply all this restriction, we have our output 2, which is the effective forest above ground biomass that we apply in this multi-criteria analysis that are in 2 main groups, vegetation and accessibility. So in the vegetation, we want to know how is the above ground biomass availability, so the amount, but also it's very important the productivity. So when we will cut this biomass, how fast this is growing, this is a very important input, and the forest cover. And regarding to the accessibility, we have the slope terrain and the road proximity. So we need to have a road close where we are extracting this biomass. So at the end of the story, the output 3 is the suitability index, which is a value between 0 and 1, and we can divide in quantile from poor to excellent. And this is an example. We wanted to understand what variables. Why? Because in the beginning, when we calculate this suitability index, the values were very low. So we identified that, for example, it was very important. This is a case of Spain. We need to normalize the absolute values. So, for example, the biomass is in megagram per hectares, forest covers in percentage, and so on. So this variable, we wanted to just transform to 0 to 1. And it was very important to check the outliers. For example, here, if we decide that the 1 pixel was 300, but was just 1 pixel, we penalize too much other pixels. So that's why we apply this threshold, and we identify the minimum and maximum value during this normalization. And then those variables were integrated in our multi-criteria analysis. Here we have positive, by the way, we apply this ramp function because you have different ways how you can normalize your variables, and those trends were positive, but in the 4-5 is opposite, because for example, in the slope, between closer we are to 0, it's much better because we are in a flat terrain, so it's much more easy to extract the biomass, and in the same with the road proximity. So between closer we are to 0, well, 0 will be already the road. To 1, it means that we are 1 meter to the road, so this is a positive case. So we create different scenarios, combine different weights, but before to decide this table with different weights, we apply this sensitivity analysis. So what we did here, we were trying to compare two variables each other and see how sensible is one variable against the other. So for example, here between biomass and slope, the trends were quite flat. So slope was almost 0. It means that it's not really a key player. So we decide, okay, the slope will be 5%, and it was fixed for all the scenarios. Productivity was also very narrow variability, 520, but then we identify high variability in the biomass, in the forest cover, and the road proximity. So this is the way how we were playing with different scenarios. So then of the story, we have this map between 0 to 1. This is just two examples between scenario 2 and scenario 5. But if you remember in our first workflow, we started deleting a lot of pixels that were not suitable for different reasons. So we got a challenge here because we have fragmentation. And with this fragmentation, we apply this clustering method where we just increase the size of the pixel. And this is more or less how we can see the clustering with the values from 0 to 1. And these are the results. And here we have the rastable suitability index. So from 0 to 1. So the green and yellow part are the most suitable places where we can allocate this pyrolysis plan. And here we did the exercise. The DNI is a value here is a kilowatts per hour meter square. And here we just wanted to see the relationship between this suitability index with the DNI. And of course, the areas that we have more vegetation, we have more rain, more water regime, so we're located more in the north, with the exception of here. So here, just these vectorial layers that we allocate just to see this example, because the DNI, we will use at the end of the methodology. I will explain soon. And here it's important to highlight that even if we play with different weights in the scenarios, the results were quite similar. There is some difference in the areas, but not too much in the mean suitability index and the number of clusters. And the largest area was in the scenario number 2 that we are highlighting here. So these red points here are the suitability index, and we wanted to optimize where to locate this pyrolysis plant. So here there is two important drivers. So first, we will not go to collect biomass more than 100 kilometers because it will be too expensive for our pyrolysis process. So we define a threshold, this 100 kilometers, and also the DNI was normalized by 1,000. So it means that we will not go to collect, to establish this pyrolysis plant in values lower than 1,000. So here we have the example in Italy. We found the potential biomass is all the biomass that we have in megagrams. Then the effective is when we were removing those pixels that were not suitable. And the proximity biomass is the biomass that we have in this radius of 100 kilometers. And then we were overlapping also with the Natura 2000, because it is important to say, okay, here maybe you have a lot of biomass, but you are in a Natura 2000 area and you need to be aware with the local restriction. So Natura 2000 doesn't mean that you cannot management, you cannot do management, you can extract the biomass, but you need to see the local regulations. And these are the more or less the result also by species. We have here 3 groups because sometimes there is a pixel that doesn't belong to pine and oaks, like it can be eucalyptus and other species. So that's why we add this extra category. So here we can see the example of Catanzaro, that is the most potential one. And you can see the values also in relative values in percentage. And now I would like to move to the residual agricultural biomass. This is just the data from the CORIN. CORIN is a land use cover at European level, and we have this vinegar and olive groves. So the aim here were determine the land through the land use cover, the area of those 2 crops, spatially, and compare also with official statistic, but each ministry in the catastrophe say, okay, how many hectares we have of olives, of grape, and so on. And then we wanted to multiply that area with the yield, that this the information is also provided by the ministry. And yeah, we have this data at provincial level, and in Italy at the moment we had just at regional. We need to see if we can do this down scaling to the regional one, and then we have this information by provincial and regional level. And then we want to identify the main companies that are processing these olives and grapes, because if we know the main companies, we know where the residues is. So this is just an example. In the case of Spain, they have this local land use cover. For Italy and Greece, we're using this CORIN, and those values are the official ones. Like in Spain, it's the Ministerio de Agricultura, Pesca y Alimentación. In Italy, they have this Institute of Statistics. And the case of Greece, they have this Hellenic Statistical of Agriculture. So those values are official. Here, we wanted to highlight the main, the 5 regions with more hectares of olive groves. And the same here with the vineyards, yeah, just to show you how they are distributed. And then, so what is about the potential of residual biomass? So here, we just multiply the areas that I show you in the previous slide by this yield, this kilograms per hectare. So we have the potential in megagrams. So I changed the units just to remove the zeros. And then we apply this factor. 30% is what we expect that remain as a residual in the case of the olives, and 21 in the grapes. So these are more or less the values by here we just select the main three regions. And this is an exercise. So because, okay, we know where, for example, in Spain, Andalusia is the region that has the main crop of olives. So where we can allocate the pyrolysis plant. So easy, we just need to identify where are the main companies. But here we got another challenge. There is a lot of association and consortium that they provide you a list of companies, so you can see the address, so you can localize them, but we don't know about the volume of these companies are processing annually. So this is the challenge that now we are dealing. So how we can get this information, and we already wrote some email to the local ministry. Maybe we'll get some information. If no, we can just keep this maybe with the CORIN and also with the satellite data, we can see, because sometimes the address is not really where they are processing the olives. They are maybe a representation office in an urban area. So we just need to select where are located, if they are located close to the crops, and decide where to. But it is much easier in the agricultural biomass. It was not so challenging like in the forest biomass, because here it's more flat, it's more clear where the crops are established. So this is just an example. We are doing the same with the vineyards for all the countries. So I think this was the final remarks. Regarding forest biomass, we have high amounts of variables, but the problem that the biomass, when we have high amount of biomass, is in areas with a high moisture regime, which is logical, no? And then also we have this restriction that we mentioned about topography, soil, and vegetation feature, and the suitability index that we obtain from this multi-criteria analysis improve when we start to define this threshold. When we did these normalization functions in all the variables, when we establish this minimum and maximum, improve a lot the results. And in the case of the DNAi, we integrate a DEN with this optimal localization for the pyrolysis plant, but we discard areas less than 1,000. And in the case of the residual agricultural biomass, the crop that we select is just olive and grape. We have more options. We have dry fruit, all other kind of crop, but we are focused on these two. To quantify was by sample, just to know the yield and just the area that the official countries provide. And to localize them, to stack this residual, it is important to localize the main companies that produce the olive oil and the wine. So at the end, we want to merge this. The potential to locate the pyrolysis plant is using these two source of resources. And thank you for your attention. And I am also open for question, discussion.
Thank you. You can stop sharing your screen.
Okay.
There are two questions for you. You have a very special role in this project, and on which points do you need to consult with the rest of the project group?
We are in the work package 4, so we are dealing with the people that need to see more the economical part. So we just quantify where the biomass is, and we provide those maps to, for example, calculate the cost to transport the biomass to this pyrolysis process.
Okay, and there is one more question. How accurately can remote sensing data capture seasonal and quality variations in biomass availability? And how is this data being integrated into supply chain planning for pyrolysis plants?
The seasonality, okay, yeah. There is new product that you can try to estimate how the biomass is growing annually. And also, if you know the productivity of the forest, you can know more or less how it's growing. But from the satellite, still is not clear if we can do this updating every year in an accurate way. And the main concern is the 3 species, because the 3 species map that we are using is a product from the European Forest Institute. So the productivity is also strongly related to the to the species composition. So now there is new sensors that we can implement to start to updating this annually, but still with high uncertainty. Because for example, one of the new sensors is JDI, but we have problem with the steep terrain. We are all the time overestimating the biomass. So yeah, but the answer is yes, we can do this seasonality and just assuming those uncertainties.
Okay, thanks. And I think in the sake of time, we have just time for one more question, and I think this is the final one. What scale do you think the industrial plant can process in tons per year?
Can you repeat the question?
Yeah, sure. What scale do you think the industrial plant can process in tons per year?
The scales mean in the amount of biomass, right?
I think so. Yes.
A single plant is hard to say because we have these numbers about the megagrams, but doesn't mean that all this biomass will be go for a single plant. So also it depends of the type of biomass. If we are talking about forest biomass, of agricultural biomass.
Maybe some of the others have some thoughts about this.
Yeah,
Giacomo?
Verena, with regard to the auger technology, the biggest size reported is 2 tons per hour. It's the biggest plant ever built for the auger. And regarding the fast pyrolysis plant, there are some examples of industrial scale reactor in Europe, such the ones of BTG, that has capacity of around 5 tons per hour. So are quite bigger in comparison to the slow pyrolysis plant. And let's say, generally, in order to increase the amount of biomass converted, these such plants can be put in parallel in order to increase the biochar or the bio-oil production. And generally, regarding the operating hours, pyrolysis plant can reach from 7,500 hours per year up to 8,000 hours per year of operating hours.
Okay, thanks.
So it's just a matter of multiply the size for the operating hours, and you can get the annual capacity for biochar and bio-oil production.
Okay.
Yeah, just if I can add, just to say that, of course, this is a very good question, and it's the question we will try to answer towards the end of the project. We have an activity devoted to the scale-up study. So the idea is to perform some analysis in order to find out the best trade-off between the pyrolyzer size, the solar part size, let's say, to get the best techno-economic indexes, let's say. But yeah, indeed, that's the goal of the project, to find out where the plants shall be located and what would be a good size for these plants.
Okay, thank you. And I think we are just in time to end this webinar. Thank you to all of you speakers and all of the attendees for joining today. And yeah, just to remind you, I will upload all the materials next week on PYSOLO.eu. And just for you to keep updated, subscribe nova-Institut's newsletter and follow us on LinkedIn. And yeah, Marco, do you want to say some final words?
No, I can just, well, yes, let's say some final words. I think, well, first of all, I thank all the people who presented at the webinar, of course, within the partners of the project. And I thank all the people who attended the webinar. I think this was just a small fraction of what we are doing during the project. So my suggestion is really to be in touch with what's happening during the project. Now we are really in the most hot part as we are testing the different components. And so please follow, let's say, the updates of the project on the website and in the other chances that there will be for sharing our results. Surely in Zaragoza in November will be a nice on-site event. So if you are in Spain or if you are interested in seeing some experimental facility as well, that is a good chance. Otherwise, of course, we will try to update the website with all the presentations and participation to conferences that we are doing in this month. Thank you all.
Thank you.
Thank you.
Thank you, guys.
Goodbye.
Thanks.
Bye-bye.
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 Bye.
Thank you.
Bye-bye.